All right, guys, we're starting Unit 6 today. Unit 6 is going to be a two-part unit where the first half of the unit is based on sequences in series, and then the other half of the unit is going to deal with some conic section stuff. So they're two kind of separate topics. We're just putting them in a unit we're going to call 6. So starting with sequences, in today's lesson, we have to be able to first define a sequence. We have to be able to create a sequence to model a given pattern. And we're going to be able to evaluate these sequences to find whatever term we want in the sequence. So I'll just be able to give a term, and you should be able to find what the value of that term is. All right, so for starters, what is a sequence? Let me define sequence over here for you guys. Okay, so a sequence is just a function. It's just another type of function. We've talked about a lot of different types of functions. This is another type, whose domain is the set of positive integers. So just to be clear, those are going to be numbers like 1, 2, 3, all the way up to whatever number we decide, but it's going to be within that set. So no decimals, no negatives, 0 is out. We're just saying we cannot plug something into this function that isn't one of our positive integers. And that's going to make sense when we start getting into some examples here. So to determine this first sequence, we've got an equation that's given. It says a of n equals 3 times n plus 2. This is going to tell us whatever term we want in this sequence. So if I want to find the first term, I'll plug in a 1 for n. If I want to find the 70th term, I'll plug in a 70 for n, and it'll tell me what the value is of that 70th term, or that first term. So A says find the first 3 terms in the sequence. That means we have to find a of 1, we have to find a of 2, and we've got to find a of 3. Pretty simple stuff, right? So to find a of 1, I'm just going to plug in a 1 for n. Same thing to find a of 2 and a of 3. And it goes on just like this, right? And I want you to really be thinking about what we're doing each time. I'm finding the first 3 terms. The third term is going to be whatever I get when I plug in a 3 for n, because n is the nth term. Notice that these numbers are going up by 3 each time. So the pattern here isn't really dictated by the number that's being added on the end. It's dictated by the number that's being multiplied by n in this case. Just like if this were a line, the rate of change would be defined by m, or the slope of the function, right? And that's what's happening here. So which term has a value of 29? Well, this is kind of the flip side of that question. If I want to know which term, then that means that what I do know right now is that 3n plus 2 equals 29, and I got to figure out what term that is. So I'll just solve for n here, right? That'll tell me which term it is. So I'll subtract 2 from both sides and then divide by 3. So it looks like it would be the 9th term. And that's just the opposite of that first question. We could use this function to determine the value of a given term, and we could use this function to determine which term has a given value. It's just like any other function. We could solve for y, or we could solve for x. So then it says, explain why there will be no term that has a value of 40. Well, just like in this previous problem, we could figure out which term would have a value of 40. And if I go through this, I'll get 3n equals 38. And then I'll have to divide that by 3 and get 12.67, we'll say. The reason that this is not possible is because, remember, right at the beginning, we defined sequences. And we said that the domain of these sequences has to be only the set of positive integers. If the question is saying which term would have a value of 40, that doesn't make sense because we can't have a 12.67th term, because the only numbers we can plug into this for n are positive whole numbers. So the reason is because 12.67 is not in the set of positive integers. Okay. Now we're going to deal with the second way to write these sequences, because we can write them like this in function notation, but we can also write them recursively. That's what this word is here, recursive. So a recursive sequence is a little different in that they're going to give you the first term. So we know that the first term of this sequence f is 20. And then they're going to say for every other term in this function, or in this sequence, take the previous term, right? N minus 1. If I'm trying to find n, this would be the term that's right before it. Take that and just subtract 4 in this case. So let's find the 6th term in the sequence. In order to do that with a recursive sequence, we actually need to find every term before it, right? So let's just try and find the 6th term. So I'll just put f of 6 over here. Well, in order to do that, I need f of n minus 1, and then I'll take away 4. I don't know f of 5 yet. So now I got to go find f of 5. Well, f of 5 is going to be the previous term minus 4, and I don't know f of 4 yet either. So you can see this is a problem. We just keep going backwards. In order to find f of 4, I need f of 3. In order to find f of 3, I need f of 2, and so on. But f of 2 we can find, because in order to find f of 2, I need the previous term, which is the first term in the sequence, and we're given that. They told us the first term. That's why this works. So if I plug in 20, which I know to be f of 1, and take away 4, then I'll get 16. And now I know that 16 is f of 2, so I can start feeding that information to the next term. Now that I know f of 2 is 16, I can plug in 16 for f of 2. And now that I know f of 3 is 12, I can keep doing this. So I'll go to f of 4. We know that f of 3 is 12, so I'm going to take away 4, and now I have 8, which means that f of 5 is 8 minus 4, which means that f of 6 is 4 minus 4. Now notice that that output is not a positive integer. That's okay, because outputs can be outside of this domain, right? Outputs are your range. So our outputs don't have to be positive integers. Our outputs could be decimals, they could be negative, they could be whatever. Our inputs have to be in this positive set of integers, not our outputs. So it's okay when we get outputs that are 0 or negative or decimals. It's not okay when we put something into these functions that are any of those things. So in the opposite way of what we just saw, now we're going to generate a function to model a set that's given, or a sequence that's given. So it says, to determine a recursive definition for the following sequence. So we've got to figure out how to define this sequence. Well, the first thing that we know is that f of 1, meaning our first term, is 3. We can put that right on the table. We already know that. And then what we've got to do is figure out how are we going from one term to the next. So I'm just going to start trying to figure out what happened here. I had a 3, and how do I get that to be a 7? In the same way that a 7 becomes a 15, or a 15 becomes a 31. What is this pattern that's happening from one term to the next? Well, to me, it seems like what's happening is the 3 is being multiplied by 2, and then 1 is added. 7 times 2 is 14, plus 1 is 15. 15 times 2 is 30, plus 1 is 31. So what's happening is every term in this sequence is being multiplied by the term before it times 2. So we're going to take the previous term, that's what this means, right? So I'll take the term before it, I'll multiply it by 2, and then I'll add 1. And that sets up the parameters for this sequence, right? And this would make sense as we go through, right? Let's try the next one. What if I plugged in, I wanted to find the 5th term. So the 5th term here, I would need 2 times the 4th term. The 4th term is 31. So if I plugged in a 31 here and multiplied it by 2, I'd get 62 plus 1 is 63. So it seems like it works. Now we need an algebraic formula, which is the other way of writing these functions for the next sequence. So this is like our initial problem. We have algebraic, we have recursive. Personally, I think recursive is a little easier to come up with when we're trying to determine an equation for it, or a formula for it. But these are the two different ways we need to be able to do it. So it looks like what's happening here is pretty basic. It looks like each term is just going up by 1. So 4, 5, 6, 7, 8, 9, 10, 11, 12. So since the rate of change here is just 1, I have a of n. My slope, or my rate of change, will be 1, right? And I don't even have to write this 1, but it's going to be 1 times n, because every number is just being, there's only going up by 1 each time. And the first term that I would put here would be a 3, and I want to explain that. So plus 3. Well, why not plus 4? Well, the reason that we can't do plus 4 there is because if that did say plus 4, then that would make our first term have to be 0, right? So let's say that said 4. And just because we know we don't need this 1 here, I'll get rid of that too. The only way for me to get the first term to be 4 is for me to be 1 less than 4 initially, because I have to add whatever the term is to it. So in this case, if I want to find the first term, just to test it, I would do 1 plus 4. That would give me 5. That can't be, because I know that 5 is not my first term. So that's why this can't be. And I've got to make sure that it's n plus 4. And let's just check to make sure that that works. Or I'm sorry, rather, n plus 3. So let's test it. A of 1, meaning our first term, is going to be 1 plus 3. That's 4. A of 2, meaning our second term, is going to be 2 plus 3. That's 5. And as we keep going, we'll get 6, we'll get 7, and so on. All right? So these are pretty dense, these notes. This is a lot of info on a new topic, but we're just going to practice tomorrow in class. And this topic is only going to last for 5 lessons, so it's a pretty short unit. All right? See you guys tomorrow.